Okay, yeah, thank you for the introduction. My name is Josephine. I'm a theorist working on various quantum technologies. And currently I live in Japan and I'm coming to you from Okinawa. So today I'm going to be talking to you about the strategies that we can use to charge open quantum batteries. From the lovely talks we've had already on quantum batteries this morning, all you need to know about a quantum battery to get meaning from my talk is that it's a quantum mechanical system for temporarily storing and extracting energy. And I'm going to be talking about a very specific open quantum battery protocol from this reference here by James and Bill, who are here. So the way this open quantum battery protocol works is it's kind of similar to the Dickey model, but we have the charger, the energy source is now, instead of the cavity mode, it's another ensemble of spins. So what we have is the battery, which is just an ensemble of spin-half particles or N2 level systems, and then we have the charger, which is a larger ensemble of spins. And initially, we might consider a case where the battery is depleted. All of the spins in the battery are in the ground state. We want to charge that battery. So what we do is we bring in a larger ensemble of spins in the excited state, and they both collectively couple to the same bosonic reservoir. And just through that collective coupling, even if the reservoir is at zero temperature, we can see the spin inversion, where the spins in the charger move to the ground state. The spins in the battery move to the excited state, and the battery is charged. So this is from this paper by James and Bill, as I said. And what I'm interested in is various modifications to this protocol. And we're going to consider which is the most efficient. And I'll talk about what I mean by efficiency later on. But before that, we need to go through sort of the physics for how this process is enabled. So I want to spend a little bit of time talking about this collective spin reservoir coupling. So we have an ensemble of spins collectively coupled to a bosonic reservoir. And in the Hamiltonian, the important thing you want to take away from this is that the interaction term contains these collective spin operators, these capital J's, and that means that the only way for the spins in the ensemble to interact with the bosonic reservoir is collectively. So effectively, what this means is that the spins, all of the spins from the perspective of the reservoir are indistinguishable. And once they're indistinguishable, we get this kind of collective coupling. Now, when we make a bunch of assumptions here by neglecting individual effects, which we don't need to, but for simplicity, the results in this talk, we will just neglect all of the individual effects, including dephasing and decay. We're also going to assume our bath is at zero temperature. Again, we don't need to, but for simplicity, we will. And once we write down the Born-Markov master equation in the rotating frame, we get this single Lindblad term here, which just describes collective dissipation. So this is the only sort of dynamics we need to charge our quantum battery. Okay, now I'm going to talk about the collective speed up that we get from superradiance. So with our collective coupling, what this allows us to do is to make use of the phenomena of superradiance. Now, superradiance is just a collective effect where multiple emitters decay much faster and with much higher intensity than single emitters. So what we have here is our ensemble of spins collectively coupled to a bosonic reservoir, and you can see they're all in the excited state. They're all initialized in the excited state. So if we want to visualize the decay process as it passes through the states, we can sort of visualize that as just seeing it relax along the ladder of Dickey states. So here we have the symmetric subspace. So all of these states that are in the symmetric subspace are permutationally invariant with respect to permutations of the spins. So if we start in the state with all excited, you can see this is the highest energy state up here, and as it decays, it just passes through the symmetric subspace. At this point, it's highly entangled, but this process happens very, very fast, and then what will happen is it'll go down to the ground state. So the important thing is that the intensity of this emission peaks proportionally to n squared, where n is the number of spins in the ensemble, and the decay time is significantly reduced. It scales with 1 on n. Okay, so we're going to make use of superradiance to charge our batteries by, instead of starting with a symmetric state where all of the spins are up, what we have here is some of the spins are in the excited state and some of the spins are in the ground state. So this is not symmetric with respect to the coupling to the reservoir. And if we visualize it on this ladder of angular momentum states, what we see is that it's comprised of components in these different subspaces. So we have the symmetric subspace over here, which we saw in the previous slide, but on this side is the antisymmetric or subradiant states. And under this collective coupling, under this Born-Markov master equation dynamics, what you'll see is the components in each of the subspaces do not interact with each other, and they just decay in each subspace to the lowest energy state as the system relaxes to the steady state. Now, what I want to say about this steady state is that it has some component of the ground state of the total system, but it also has these dark states, and these dark states have some energy associated with them, and it is those dark states that allow us to make use of this this collective coupling to charge the batteries. So in the steady state, the battery will have some energy in it because of these dark states. Okay, so now we can go on to seeing these dynamics sort of play out according to just, simulating the master equation. So there's 2 scales that we can look at these results on. So the small scale, we can just directly solve the master equation. And for the larger scale, we can perform a mean field approximation. So at the small scale, we can solve the master equation and get these results for the energy capacity for each of our spin ensembles. So the pink line is always the charger and the blue line is the battery in this case. We've started with a fully charged charger and a fully depleted battery, and we've ended with the battery being almost fully excited. So what we need for the battery to be fully excited is to have a large disparity between the spin populations in the charger and the battery. So the bigger the difference, the more we'll see this excitation. And that's what I'm looking for when I say efficiency. I want the energy capacity to fully pass from the charger into the battery. Okay. For the large-scale results, we can perform a mean field approximation, and with this, we can access the dynamics of this system for much, much larger scales. So what I have here is 10 to the 4 and 10 to the 2, and you can see in this case the battery is fully excited, and we'll see that whenever we have this huge disparity between the spins in the charger and the spins in the battery. Okay, so this is all work that has already been done. What I'm interested in my work is to sort of extend this, and the research question that we can think of to motivate this is to how can we use this process to charge multiple batteries? So this might seem like a little bit contrived, but what it will actually lead us to is a lot of interesting conclusions for how we can use this mechanism to control the flow of energy in our system, and also how it limits the flow of energy in our system. So the simplest sort of thing you might try first is to just use this to charge multiple batteries in the same cavity. So just shove as many batteries as you can inside the one cavity. And on the small scale, what we'll see when we look at the energy capacity. So for example, this is 10 spins in the charger, 3 spins in the battery. And on the blue line here, we have the energy capacity. If there's one battery in the cavity, we have now there's 2 batteries in the cavity, and now there's 3. So you can see the energy capacity decrease each time. And this is because the total number of spins in the battery is, in all of the batteries, is 9 versus the 10 spins in the charger. So on the small scale, if we want to use this method, we need to compensate the number of spins in the batteries with a larger charger. But if we want to do this on the large scale, where there's maybe 10 to the 4 spins in the charger and 100 spins in the batteries, if I produce this plot again, all of the lines will overlap. So on the large scale, this is fine. On the small scale, you just need to compensate for this adjusted spin population. Okay, so the next thing we might want to do is maybe there's different batteries located at different spots, maybe spatial locations, and we want to have one central charger that can flow energy to many, many batteries. So we're going to look at this charging in parallel with multiple cavities. So to start with, just to benchmark this, we'll use a single cavity with 6 spins and 1 spin, and this is the energy capacity of this. And now we're going to introduce another cavity, another battery, but the spin populations of the remaining system is the same. And what you can see here is this huge disparity, this huge decrease between the efficiency, the energy capacity of the battery in the steady state here, and the energy capacity of the batteries in the steady state for the 2-cavity case. So just by introducing another cavity into the system, we have this other decay channel, and we've significantly reduced the efficiency. We can't really even transfer as much energy. Okay, but so we might conclude from this that we cannot efficiently charge in parallel with multiple cavities, but what we need to look at before we conclude that is, of course, the large-scale results. And this is quite interesting, I think, because so on the top here, we have the result from the previous slide. On the bottom here, we have the large-scale results for 10 to the 4 and 10 to the 2 in each of the batteries. Now, what's interesting about this plot is that we still, of course, are getting the collective speed up from the superradiance, but we literally cannot transfer enough energy into the batteries for it to reach the energy capacity of 1. So it's not efficient in terms of the energy that we can transfer. And this is sort of reminiscent to these other nice works, which also look at charging in parallel with multiple cavities. But so in here, we are still seeing the collective speed up, but we're not seeing efficient energy transfer. Okay, so I'm also interested in the entanglement and how we can sort of look to the entanglement as sort of an artifact of efficient charging. So we're going to look at the entanglement between these systems, and again, we'll sort of benchmark this with the single cavity charger and battery. And this is the entanglement of this system in the steady state. This is the log negativity. And if we have the 2 cavities now, there's sort of multiple bipartitions that we can do. So the first one is the entanglement between battery 1 and the charger. The second one is the entanglement between the charger and battery 2, and these are equal because, as they should be, because everything is completely symmetric. But what we see from this situation is that the entanglement between the charger, where we want to transfer energy from, and the battery, where we want to transfer energy to, is severely diminished just by presence of that second cavity. But what we have done in this situation is inadvertently optimize the entanglement between the battery and the other battery. So just in this system, and just with the presence of the charger and the collective coupling to zero temperature reservoirs, we can find some strong entanglement between these spins on the outside. But that's not where we want to sort of transfer energy to or from. But the interesting implication is that if we follow that thought and we sort of look to that setup to use to transfer energy, we can then see efficient energy transfer. So this is charging quantum batteries in series using multiple cavities. And this is maybe the only way that I've found in this research to use multiple cavities and find this efficient energy transfer. It's the flow of energy is going from the charger into battery 1, into battery 2. And this requires this sort of configuration where the number of spins in the charger is much greater than the number of spins in battery 1, which is then much greater than the second battery as well. And if we look on the large-scale dynamics for the energy capacity, we can see this full excitation of the first battery and then the full excitation of the second battery as well. So this is very efficient. This is exactly what we want. But I will, of course, note that this is not really charging multiple batteries. We're using one battery to charge the next. But it's very nice that we can fully excite the batteries in this chain type of situation. Okay, so of course, let's go to the entanglement again. And I think we find something very interesting and very confirming about the flow of energy in this system. So if we look at the small scale dynamics here, this is a very small system of 8, 2, and 1, we can see the entanglement between the charger and battery 1 is in this purple line here, and it spikes when the energy is being transferred, and then it reduces down again. And then the entanglement between battery 1 and battery 2 sort of grows to its value in this steady state. Okay, so with that, I've come to the end of my presentation. I just want to leave you with a concept for what are the implications for this work. So we're looking at these batteries to charge quantum devices, possibly. And what I want to suggest is maybe we can use these quantum batteries to charge devices along a network, where the nodes of the network are spin ensembles, or these batteries, and the channels connecting the nodes are collective environments. So we know that we can't charge in parallel with multiple cavities. We know that we can charge in parallel with a single cavity, but we can charge efficiently in series, but we need that specific spin population configuration of one spin being of the charger being much bigger than the second battery, which is then much bigger than all of the other following batteries. So with that, I want to thank my collaborators and thank you all for listening. I'm happy to take any questions.
Excellent. Any questions?
Thank you for the very informative talk. So reflecting on the question in the last session from our friends, not repeating the same thing, I'm wondering when you, looking at different scenarios in your work, do you also consider how stable that energy is to keep that battery energy or whatever charge, or you just look at the amount of the energy? So how can you keep it stable, can be stored there? And I know that it's already mentioned that discharge is at this stage is a bit problematic.
Okay, so if you want to store the energy in these systems, what you do is just put a dephasing pulse on the ensemble, and it destroys the coherences, and you can keep energy stored there for a while. But the other thing I will mention is that if these batteries are implemented with large enough spin ensemble sizes, then the steady states that I've shown are quite stable until the individual effects occur. So for really, really large systems, this will happen much faster. The collective effects will happen much faster than the individual effects, and should be stable in that time. But that really depends on the size of the system.